Hey, Mr. William, why you look so stressed?
I'm trying to draw this dot and cross diagram that my student asked me. It's very difficult to draw. I know how to draw, but I don't know what's the best way to explain to the student.
Dot and cross,
Yeah.
Very easy one. I got a secret technique I mastered over the years already.
Secret
technique.
Why?
Yes.
I don't know. You know the secret technique?
You want to learn or not?
Yeah, of course.
Okay, can. But this secret technique, I need 2 tutors to teach one. One tutor
tutors?
cannot teach one. Need 2 tutors. So I must call my buddy, Mr. Tim in.
Oh,
Can
really?
I?
Okay, sure.
Mr. Tim, come here.
Oh, Tim.
Mr. William wants to learn the secret technique in drawing dot and cross diagram. The secret technique, you know, right? Yeah, solid show, what one?
You all look very shady, What are you trying to do?
No, now don't worry, it's a good technique. You learn it, you'll be very happy.
Okay, then I can teach my student, right?
Of course, you can teach your student. Of course,
okay, sure. I'll teach them over the
But for
weekend.
this secret technique, you must be relaxed, you must be calm. So you need to close your eyes, okay, meditate a bit, relax a bit. Okay? So it's like trust the process. Trust the process, okay?
Okay.
Close your eyes, okay,
Don't
relax,
do anything strange,
You'll feel some tension on your shoulder, on your face, but it's all normal, all part of the process. Okay? Then, so I'm going to start teaching you the technique now.
Alright.
Okay, so you want to draw the dot and cross diagram, right? So Mr. Tim now is massaging your face. So you will draw your dot.
Hey, Tim. Quite good,
Okay, yeah, sure, right?
Yeah.
Draw the dot. Okay, draw
You can
finish the
work-
dot.
Yeah. You can work with
You
the
will
massage
draw
center.
your cross.
Quite good.
Okay, sure or not?
Yeah, quite good, quite good,
Okay,
quite good.
done ready, done ready.
Done ready?
Yes, done ready.
Where's the answer?
Then you take a look.
One eternity
I think you didn't use permanent marker.
Yes, yeah.
Handsome or not?
Handsome, but I think just not more handsome.
Hey, filming start already?
Okay, serious.
Okay. Hi guys, welcome back. Remember who we are? We are the
Chemical Bonding Brothers!
Alright, now for today's lesson, we're just going to focus on one thing, alright, one very important concept for everyone, which is how to effectively draw dot and cross diagram at A level. Now, we're going to show you a strategy to effectively draw most of the dot and cross diagram in just 4 steps, right? 4 steps can allow you to draw most of the dot and cross diagram.
Oh, that's amazing.
Alright, now you look at your notes, you do find that there are 4 steps over there. Now what I'm going to do is I'm going to use an example to walk you through the 4 steps. And what example am I going to use? I'm going to use this example in your notes, which is PCl₃. Right? So when you do dot and cross diagram, you must be able to identify this thing called the central atom and also this thing known as the terminal atoms. Right? So some rules for us to follow. You can see, how do I know who is the central atom? As a general guide, either we are the least electronegative atom, you can be also the single atom. So for example, if you have PCl₃, you notice P is a single atom. So what we're going to do is we're going to put P in the middle, and then we are surrounded by all the chlorines, which will term them as terminal atoms. Now, after you have identified the central and the terminal atoms, the next thing you got to do is you have to ask, what is the bonding between them? Is it going to be a single bond, double bond, triple bond? There are many ways we can try and error. But the whole idea is to give them the stable configuration, which typically could be the octet or the duplet configuration. Alright, so let's say we're going to focus on chlorine as the terminal atom. You do notice chlorine is in group 17. That means he has what, 7
Valence electrons? Yep.
So how many more does he need to be stable?
Alright, 7 needs 1 more to become 8, so you need to form 1 more bond.
Yep, so you need just 1 bond because you already have 7 electrons. I just need 1 more covalent bond for me to be stable. Right, so this is what's going to happen. We have here 7 electrons. So I'm just going to do a single bond between phosphorus as well as chlorine. And the same thought process must be replicated for the other 2 chlorines as well. Okay, so this is what we're going to do. Okay, so right now, as you focus on all the terminal atoms, you do find that they all have that stable octet configuration, but your attention should now be focused on the central atom. Alright, now you do notice there is a point below. In point 4, the total number of electrons must correspond to the group number. And phosphorus is, I think, in group 15, so there should be 5 valence electrons. But how many has been used so far for the dot and cross?
3?
Yeah, we have used 3. You can see that there are 3 dots over here. Alright, so there are 2 more missing electrons, which we are expected to pair them up as lone pairs. So lone pairs will refer to unshared electrons, right? So what we do is we just put them together as a lone pair of electrons. Alright, so once you're done with this, just do one final check. Make sure the terminal atoms, they have the stable octet configuration, and also your central atom, all the electrons has already been accounted for. Right, so this is the simple rules, how we can draw the dot and cross diagram. Right, so I'm doing the easy ones, and I'm going to bring the difficult ones to Mr. Yap, who will walk us through.
Right. Okay, so let's bring our attention to part C. So part C uses H2CO. So as you can tell, there are three elements here. So H will never be the central atom. So between carbon and oxygen, the less electronegative one will be the central atom. So in this case, carbon will be the central atom. The next step is to position the terminal atom. So you can just put them around carbon. So O and H surrounding the carbon. Now the next thing is, you guys should know that oxygen has 6 valence electrons, so it only needs to form 2 bonds to achieve the octet configuration. Carbon has 4 valence electrons, so it needs to form 4 bonds to achieve the octet configuration. Hydrogen only has 1 valence, so it just needs to form 1 more bond to achieve the duplet configuration. So with this in mind, therefore you should be able to deduce that oxygen will form a double bond with carbon. Alright, so oxygen is in group 16, so there are 6 valence electrons. I only use 2 for bonding. How many more must I draw?
2 more.
Two more pairs, you mean?
Yes, 2 more pairs.
So 4 more electrons surrounding the oxygen. Then the third valence electron of carbon will be used to form a single bond with hydrogen. All right. So does hydrogen have any more lone pairs, William?
No.
No?
Hydrogen is like, there's only 1 valence electrons around it.
You're absolutely right. So the last bond will be a single bond between this carbon and the right hydrogen. Right, so after drawing, just double check that all your valence electrons are in. So carbon has 4 valence electrons denoted by the 4 crosses. Oxygen has 6 valence electron, 6 circles around it. So everything is fine. Right, so this is how we draw H2CO. Okay, so with that in mind, let's look at the fourth example, part D, C2H2. Okay, so once again, there's 2 elements. H will never be central, so there's only carbon. So the 2 carbons will be side by side. Alright, then the 2 hydrogens, we have to split them equally, so 1 on each side. Okay, so same thing, 4 valence for carbon, 1 valence for hydrogen. So as seen in part C, carbon wants to form a maximum of 4 bonds. So hydrogen only 1 bond. With that in mind, you should not have to infer that the bond between the hydrogen and carbon would be single bond. Alright, and the bond between the middle carbons would be a triple bond. So this middle carbon will use 3 of its valence electron to form a triple bond with the other carbon atom. Alright. Okay, so then lastly, the hydrogen on the right hand side will form a single bond with the carbon. Okay, and it will look something like this. Okay, so William, you notice, right? There are only 2 elements. Sorry, there are 2 elements, but there are 4 atoms. How many symbols am I using altogether?
Right now you're using 2 symbols.
2 symbols, right? Why am I only using 2 symbols? Because this diagram is called a dot and cross diagram. So you can only use a dot and a cross. You don't go and give me a lot of pattern, draw diamond lah, triangle lah, square lah, okay? Usually we don't, it's frowned upon using all these additional symbols. So literally we will only use dot and cross. So if this hydrogen electrons is denoted by a dot, the adjacent element, right, this carbon will be a cross, and then the adjacent one, this carbon will be denoted by a dot, and the adjacent one will be denoted by a cross. So what we are doing is we are simply alternating, okay, between dots and crosses. Right, so this is how we would do it in A level. We will usually only use dots and crosses. So if you want to represent electrons from different atoms, you alternate them.
Yeah, if you use too many patterns, there's a popular saying, right?
Popular saying, pattern more than badminton.
So try to
so
avoid
don't do that.
right?
Okay.
Alright guys, now there's some very special dot and cross diagram that's very often tested at the A level. So if you flip to the next page of your notes, you will see this thing called electron-deficient centers. Right, so that dot and cross diagram, you'll find that the central atom doesn't have 8 electrons around them. Right, so it says there, there are central atoms with less than 8 electrons around it. So who are very popular for this? Usually beryllium compounds, group 13 elements. They are notorious, very well known that they don't have a full octet structure. Okay, so one example is this. You look at this guy, BF3, right? So boron, remember, is in group 13 of the periodic table, and then fluorine has 7 valence electrons. As we had explained earlier, you will usually do a single bond with all the fluorines to make sure that they have the stable octet configuration. And you do realize boron has already utilized all his electrons in the bonding, right? So there's no more additional electrons, but the total number around him is only 6 electrons. So this guy is electron deficient because he is not yet an octet. He has a space for 2 more electrons to come in, right? So these are some examples of electron deficient center. Now, there's an example below. Let me walk you through, right? So you'll see this BeBr2 Bieber, we call this, all right? Not Justin Bieber, all right? So, all right, I'm going to draw BeBr2. Okay, beryllium, which group is it?
2?
Yep, group 2, right? So we do expect beryllium now to be the central atom, and then there will be 2 bromine that is going to be surrounding atoms. And because beryllium is in group 2, there will be 2 valence electrons. And remember, all the halogens, they will just require 1 covalent bond between them to give them the octet configuration. So we do expect now the terminal atoms to be already stable. Now, beryllium has exhausted all his electrons, but you do notice he has only 4 electrons around him. So again, it's not a very stable octet configuration, but certain molecules just happen to be like this, right? So it's very good for you to be aware what are some common examples, right? Typically, your beryllium compounds, boron compounds, group 13 elements, they're very well known to be electron deficient, right?
Okay. Now, so another special case that you will see is what we call an odd electron species. So some species, they are unable to achieve the octet configuration simply because they do not have enough electrons to make it to 8. So if you look at the 4th bullet point, some common examples will include the nitrogen dioxide and nitrogen monoxide. So what's one way to tell that they are odd electron species? So nitrogen is in group 15, it has 5 valence electrons. Oxygen is in group 16, so 6 valence electrons. So in NO2, the total number of electrons involved in the valence shell would be 5 plus 6 plus 6. So William, I know your math very good one. Can you tell me 5 plus 6 plus 6 is how much?
5 plus 6 plus 6 is 17.
17. 17 odd or even?
17 is odd.
Odd number, right? So this is one quick way to tell whether something is an odd electron species. You add the total number of valence electrons involved in all the atoms, right? So another example, NO, 5 plus 6, 11. So that's an odd number. So this is what we call an odd electron species. Okay, so let's look at part B, and I will use part B to explain a few more terms to you guys. Okay, so nitrogen monoxide, NO. So there's only 2 atoms involved, so they must be side by side. Nitrogen 5 valence, oxygen 6 valence. So oxygen with 6 valence electron only want to form 2 bonds, so you would share both of its electrons with nitrogen. Add in your lone pair, so 4 more electrons around oxygen. Then nitrogen is group 15, right? So I already used 2 for bonding. How many more must I draw for the lone pair?
3 more.
3 more electrons, so 2 of them will be paired. And the last one, like no friend, so nobody to pair with. So it will very lonely. So it will be an unpaired electron. And if you were to count the total number of electrons surrounding nitrogen, there's 1, 2, 3, 4, 5, 6, 7 electrons. So it has not achieved the octet configuration, and 7 is an odd number, so this is what we call an odd electron species. Okay? And since a species with an unpaired electron is given a special term, it's called a radical. Alright guys, so another example would be species that expand their octet. So if you guys recall your atomic structure, the 3rd quantum shell can hold a maximum of how many electrons?
18 electrons.
18 electrons, wow, that's quick. Alright, faster, very fast. Alright, so the 3rd electron shell can hold a maximum of 18 electrons. So elements from period 3 and below can actually expand their octet. Expand their octet simply means they can accommodate more than 8 electrons around them. Okay, and the reason for that is because they have what we call energetically accessible vacant d orbitals. So in the exam, if you were to explain why something can accommodate more than 8 electrons around them, you would say that they can expand their octet, but please do not stop your explanation there, because expansion of octet is a very informal term. The proper chemical principle behind it is because they have d orbitals, they are vacant. Vacant simply means it's empty, so they can accommodate electrons in it, and the orbitals are also energetically accessible, which means they are low-lying, sufficiently low-lying that they can participate in bonding. Alright, so you have to give this entire phrase. Right, energetically accessible, vacant d orbitals, to explain the phenomenon of expansion of octet. So common examples include PCl₃ and SF6. So if you were to look at the 2 examples below, phosphorus is the so-called single atom here, so it will be placed in the center, chlorine around it. So phosphorus is from group 15, 5 valence electrons. So it will form 5 single bonds with the chlorine. Altogether, around the phosphorus now, there are 10 electrons. So 10 electrons, obviously more than 8. So yes, what we call expanded is octet, and it's perfectly fine because phosphorus is in period 3. Right? Similarly for SF6, sulfur is in group 16, so 6 valence electrons, forming 6 single bonds with fluorine. So there are a total of 12 electrons surrounding the central sulfur now. So yes, expanded is octet, but it's perfectly fine because sulfur is in period 3 and below. Alright.
Alright, so the last portion which I'm going to do with you guys, okay, this is actually quite complex, which is the formation of what we call covalent ions. Right, so you can see over there, it says in polyatomic cations or polyatomic anions. Now the word poly means a lot, alright, so you're going to expect a lot of atoms within the ions itself. Okay, so let's go through bit by bit. Maybe I'll start with anions, right? So we have an example over here. This is sulfate, SO4 2-. Now when you see a negative, what does negative usually means?
So if a particle has negative charge, means there are more electrons than protons. So there are more electrons now.
So that means he has received some electrons.
Yeah.
Alright, so I'm just going to use very layman's term here. This guy has gained electrons, right? So if there were 2 electrons that's going to be gained, I think it makes perfect sense for the electrons to go towards the more or the less electronegative atom.
So more electronegative, right? Because electronegativity means the ability to attract bonding electrons to yourself.
Yeah, to suck electrons.
Yeah, suck electrons, right? Yeah.
Electrons. Okay, so what's going to happen now is you notice we're going to accept 2 additional electrons. And the practice is always to split the electrons, right? So for example, what is happening now is you expect one of the electrons to be moving towards this oxygen and one of the electrons to be moving towards this oxygen, right? It's best for you to split the negative because it's very unstable for that same atom to hold double the charge. So it's best for us to split the electrons up to distribute the charges. Therefore, you will want to see this oxygen not as a typical oxygen because it has received an additional electrons. Right, so you will see this guy something like a 7-electron species, so something like a halogen, right? And usually, how do we bond with halogen?
Because 7, right? You only need 1 more, so you form a single bond.
Yep, you form a single bond, right? Which is why you notice this is a little bit different from a typical oxygen. Usually, we'll be forming double bonds, but because it acts like a 7-electron species, this 2 will be doing a single bond instead. All right. Now, the last oxygen or the last 2 oxygen you notice will return back to the usual. They have 6 electrons. They're just going to need 2 more electrons to give them the octet configuration. So what will happen is they're going to do a double bond. So the double bond will give them the octet structure. And one more time over here, the double bond will give them the octet structure. All right. So once all this thing is in place, the last thing that you must check for is to ensure that your central atom, in this case, which is the sulfur, has contributed 6 valence electrons into the chemical bond, right? And you do notice there are 6 crosses over here, which will symbolize 6 electrons used by sulfur. Do notice sulfur has expanded the octet configuration, but it's okay,
perfectly
right?
fine,
It's
right?
perfectly fine
Yep.
because this guy is beyond period 3 or period 3 onwards. They have your low-lying accessible 3D orbitals to make sure that you can expand the octet structure. All right. So the general idea, if I were to consolidate, you always focus on the charges, right? If you have a negative, you distribute the additional electrons to the more electronegative atoms, right? And in converse, if you have something that's positively charged, right? A cation means you are going to
Lose electrons.
yeah, you're going to lose electrons, right? So I have to take 1 electron away from somebody here. So should I take from the more electronegative or the less electronegative?
So in this case, it's the opposite. So the less electronegative one will be more willing to give up its electron. So you'll be lost from the less electronegative element.
So the lousiest
Yeah.
sucker, right?
Yeah.
It's going to lose its
Yeah.
electrons away, right? So in this case, you do expect your sulfur to be the one that is going to lose its electrons. And what does that mean? It means that sulfur typically will contribute 6, but because it's losing 1 electron away, so this time around it's just going to contribute 5 valence electrons, all right? And yet again, you find that the fluorine are the terminal atoms. So with fluorine as the terminal atoms, you'll always be doing a single covalent bond between them, right? And then you check your sulfur. Your sulfur has used 3 in a covalent bond, right? Remember, this guy is going to contribute 5. So there are 2 more, which is going to be paired as a lone pair. All right. So in this case, your sulfur didn't really expand the octet structure. There are 8 electrons around them. It has a stable octet configuration. All right. So the key thing, as we have been saying many times, focus on the charges, decide who gains or who loses the electron, follow back the rules that has been explained earlier. Who is the central atom? Who are the terminal atoms? And then just make sure that the terminal atoms will fulfill the octet configuration. All right. So these are some of the general rules, the general principles behind how we draw the dot and cross diagram. And knowing this is just, I think, the start of everything, right?
Yes.
It's really about what must they do.
Practice.
Yes, you really have to practice a lot, right? So dot and cross is really a practice thing. So what we have for you on the next page is there's several questions. Okay, we will be showing you in class how we will run through the thought process And in the questions that's going to be upcoming, there will also be a lot of similar questions for us to practice. There is no shortcut for this chapter when it comes to electrons. It's really just practice, practice, and practice.
Yes.
Okay, so let's do this together in class later this week. Right, so we look forward to seeing you in class. Okay, but remember who we are. We are
The Chemical Bonding Brothers!